Okay, well, I'm going to welcome you all to Ryoka's third anniversary. For those of you who don't know who Ryoka is, we are the Renewable Energy Owners Coalition of America, which is a group of solar owners and renewable energy advocates. We were born right here in Pueblo 3 years ago, almost to the day, February 20th, 2018. We started as a response to what we viewed as unfair treatment by our investor-owned utility towards solar owners. We felt that they were trying to raise our rates unfairly. Our mission is to protect and promote rooftop solar. My name is Roz De Lizaraturi, and along with my husband, Manny, who's running the technical right now, we are the co-founders of Ryoka. As you will hear this evening, rooftop solar can and will be instrumental in helping mitigate climate change. We are very excited to have as our keynote speaker, the eminent Dr. Scott Denning. Hold on a second here. I gotta get my cursor. Dr. Denning is a Montfort professor of atmospheric science at Colorado State University. He's author of more than 100 papers in the professional climate literature. Dr. Denning served on advisory panels for the U.S. Department of Energy, NASA, NOAA, and the National Science Foundation. Dr. Denning has spent a good portion of his professional life studying climate change. He's going to focus on the 3 S's of climate change: simple, serious, and solvable. Now, I know you're all going to have a lot of questions, but we have a chock full agenda tonight. So if you all wouldn't mind, we have a chat available for you. If you could put your questions in the chat, and if we can't get to them this evening, we will definitely get to them in an upcoming newsletter. We'll make sure everybody knows your questions and the response to them. So without further ado, the reason a lot of you are here is to hear Dr. Denning. Dr. Denning? Take it away.
Thank you. Thank you very much for having me. I'm going to share my screen if I can get a, oh, no, it says host disabled participant screen sharing. So somebody's going to have
Just a moment. Okay, try it now, sir.
Okay, we'll give that a shot. Yeah, it's not working. It's working.
Hey.
So I had 3 things to talk with you about, and they all start with the letter S, so it makes it easy to remember. The 3 S's of climate change are simple, serious, and solvable. And simple is kind of how does it work, and serious is why is it bad, and solvable is what are we going to do about it. So try to spend about equal time on each of the S's. You might think it's a little odd for me to say that climate change is simple because, you know, I've been working on it for 30 years. And if it's so simple, how come I still have a job? But it is actually basically the science of climate change is stuff that you learned in grade school. And I'm just here to remind you about it. Unfortunately, then we're going to have to talk about how bad it is. That's the serious part, but we will get to the solvable. I promise that we will get to solutions and I will not leave you, you know, crying in your beer. So did you ever wonder why day is warmer than night? Or why summer is warmer than winter? Or why Phoenix is warmer than Fargo? You probably haven't really wondered about it because you kind of already know why these things are. And what I'm going to tell you is that the answer to these 3 questions is all the same answer. The reason why a day is warmer than night is because heat in minus heat out equals change of heat. If you put more heat into something than you take out, it warms up. And if you take more heat out than you put in, it cools off. So this is exactly why the sun beats down on the ground during the day and it gets warm. It's the same thing for the Earth. The Earth warms up and cools off just like everything else. Now, when we have different weather, like today it was really warm here and tomorrow it's supposed to be really cold here, that's heat coming in and out the sides. That's the weather. The day-to-day changes of the weather are, you know, an air mass blows in from Canada or something, and we're replacing the air with different air. But when you look at the climate of the whole world, there are no sides, right? The world is round. So no matter how much the heat moves sideways on a round ball, it doesn't change the total amount of heat. The only way that the Earth can change its total amount of heat is through the top. And by the top, I mean the top of the air, the top of the atmosphere. So the incoming heat, everybody knows about that, right? That's the sun. But if that was the whole story, That's just heat in, right? Heat in minus heat out equals change of heat. So the Earth would get hotter and hotter and hotter until it like melted and boiled and vaporized. That can't be the whole story. There's got to be heat getting out, and the heat gets out also through radiation, just like the incoming sunshine, but the outgoing heat is in a part of the spectrum that we can't see. It's the infrared part of the spectrum, and it's invisible to our eyes, but it's totally there. Like if you've ever turned on a stove, electric stove, you can feel the heat radiating off of that burner before you can see it, and that's infrared radiation. So the thing is that the outgoing heat that goes out can't get through the air very efficiently. The air is transparent in the visible part of the spectrum, otherwise you wouldn't be able to see. But the infrared blocks some of that outgoing heat. And the reason is because, now this part maybe you didn't learn in grade school, the air is made of molecules, and almost all the molecules are these, two kinds right here. The top one you know all about, that's oxygen, O2, and the bottom one is nitrogen, N2. And the thing about those molecules, they can interact with the heat rays, but up comes this infrared ray. It's actually electromagnetic radiation, and the molecule is two atoms of the same element that share some electrons in between. That's a chemical bond, and again, high school stuff. But the electrons can catch a hold of that oscillating magnetic field, and they go back and forth. It's like the molecule gets longer and shorter, kind of as if it sings, like woo, woo, woo. Not really, it doesn't make that sound. I just make that part up. But you can imagine the wiggly molecule has now converted some of that outgoing radiation into the vibrational energy of the molecule. But because 99% of the molecules in the air are just these two kinds, that's the only way they can wiggle, the only dance they know, the only way you can change the geometry of a two-atom molecule is by making it longer and shorter. There's a tiny number of molecules in our air that have 3 atoms instead of 2. And by far the most abundant ones are this one at the top, carbon dioxide, and this one at the bottom, which is called water, H2O, right? So the reason why they're different is because they've got different ways to wiggle. You can imagine that same photon or, electromagnetic wave coming up, and it hits that molecule. I only have the 2 hands, so let's let my head be the carbon, and then there's an oxygen here and an oxygen here. And along comes that wave, and it can wiggle the molecule, so it goes woo, 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 or can then emit a photon back to its ground state, woo, woo, woo. But there's more, because unlike O2 and N2, it can go wee, boom, wee, boom, wee, boom, wee, boom, whoop, boom, whoop. Each one of these different ways of wiggling that molecule will absorb a slightly different wavelength of infrared energy, a slightly different energy level of photon, and that's what makes CO2 a greenhouse gas. It's not greed or capitalism or Al Gore. It's just bad luck that the gas that comes out when we set carbon on fire has 3 atoms instead of 2 atoms. And there's all these different ways you can wiggle that molecule that absorbs different wavelengths of infrared light. So the air is actually partly transparent. It's transparent to the visible part of the spectrum, but those CO2 molecules and the water vapor molecules slow down the outgoing radiation so that it can't get out. So you've probably seen the cartoon before. The sun beats down on the ground. Some of it reflects off to space, but the part that doesn't reflect off gets absorbed at the surface, and that's warming the ground, right? That's heat in. So that heat's got to get back out, and that's these red arrows, the infrared energy. Some of it does get out, about 5% of it gets out, but 95% of it gets stuck. It goes up part way, and then it hits one of these wiggly molecules that stops it and gets transformed into the vibrational energy of the molecule, get re-emitted. Some of it goes up, but some of it comes down. And that downward radiation from the warm sky is actually more important source of our heat than the direct sun, because of course the sun is only up during the day, but the sky is there 24/7. So this is actually the greenhouse effect. It's the downward radiation from the sky, and it's a huge contributor to life on Earth. We couldn't be here. The Earth would be a frozen ball of ice without that extra downward heat coming from the wiggly molecules in the sky. So it leads me to what I call the common sense explanation of global warming. Many of you are old enough to remember these things. This was an incandescent light bulb back in the day. And these little bitty ones like this, these were 4-watt light bulbs, right? So these were like night light bulbs that we, back when I was a kid, we used them for Christmas tree lights. And then when my kids were little, we used them for night lights, and you'd put them in the hallway so they could find a bathroom, right? So you remember these little bitty 4-watt light bulbs. So if you double the number of these beep boo molecules up in the sky, it would add this much heat, 4 watts, to every square meter of the world. So like look around you and find something that's about a square meter. So like for me, it's my desk, and I can imagine a night light bulb here, another one over there, and over there, and over there. Oh, but it wouldn't just be my desk or my room. It would be not just all of Colorado, it'd be the whole world covered with little 4-watt night light bulbs every 3 feet. And if you did that and you left those night light bulbs on 24 hours a day, 365 days a year for the rest of your life, by gosh, that would make the world a little bit warmer. And maybe not a lot, because they're just night light bulbs, but there's boatloads of them. They're everywhere. There's every 3 feet a 4-watt light bulb. Believe it or not, all of that was known before light bulbs were even invented. This whole story about the wiggly molecules and the absorption of the outgoing heat was discovered by this guy, John Tyndall, back in the 1860s. So 160 years ago, they worked out the physics of the absorption of infrared light by CO2. He put CO2 in glass bottles and he shined light through it, and he measured how much absorption was from different gases at different concentrations. And he actually wrote a famous paper 160 years ago predicting that if we burned enough coal, we would warm up the world by adding all the CO2 to the atmosphere. So this is not something we figured out lately. This is something we've known for hundreds of years. In fact, kind of common myth number one about global warming is that the reason us scientists are so sure that this is going to happen is because it's been warming up lately. And for sure, it has been warming up lately, right? It used to be cooler, and this shows like kind of temperatures rising and then rising even faster. And all that is true, and that is because of CO2, but that's not how we figured this out. You look at a graph like this and you think, oh, first it got hot and then they started blaming CO2 for it. But no, we knew this was coming 150 years ago. We know that adding CO2 to the climate will warm the world because we know that when you add heat to things, they warm up, right? This is like totally obvious. You put a pot of water on the stove and you put extra heat in the bottom. What does it do? It changes its temperature. The world works just that same way. This is the same physics that warms up days compared to nights or summers compared to winters. We're really sure about this. This is a very, very well understood phenomenon. So now we got to talk about serious. We got to talk about why this could be a bummer for us going forward. One of the reasons why is it could get quite a lot warmer. So here's like how much warmer it's going to get if we burn a little bit of fuel or a lot of fuel or a lot more fuel. The first thing I want you to notice is that the land warms up more than the oceans. That's because the oceans are really deep and they suck up a lot of heat. It takes a lot of light bulbs to warm up 13,000 feet of water. The next thing, if you look, the north warms up more than the south. That's because the south is mostly ocean and the north is mostly land. And the third thing, if you look, the snowy, icy places warm up even more than the not snowy, icy places. And that's because snow and ice is bright and white. It reflects the sun to space. So if you warm it up enough to melt the snow and ice, then you soak up some extra sun, and that gets added to the extra heat from the CO2. So do you happen to know anybody who lives on land in the Northern Hemisphere where it snows? Oh yeah, all of us, right? We get extra. We don't just get global warming, we get extra. So if we stop burning stuff right away, we'll get maybe 3 degrees Celsius of warming. If we keep burning throughout the rest of the century, we'll get more like 6 degrees Celsius. Oh, but wait, that's Celsius degrees, and you guys all do Fahrenheit at home. So convert that to Fahrenheit. It's more like 5 if we stop, or 10 Fahrenheit if we don't stop. That's actually quite a lot. 10 degrees Fahrenheit. I don't know, was it like 60 out today? 10 degrees Fahrenheit be 70. I'd probably be okay with that. But we're not talking about just today. We're talking about on the average 10 degrees Fahrenheit of warming. So the only way to get your head around that is to look at a map. So here's a map of the United States with high temperatures in Fahrenheit, and each color on the map is 5 degrees Fahrenheit warmer. So if I slide each of these little cities two colors on the map, that's like 10 degrees Fahrenheit of warming. So Denver's moving to Albuquerque. I don't know, you guys in Pueblo, you're moving to something like El Paso. That's a lot. That's like if you were a farmer in Eastern Colorado and you swapped out the temperature of El Paso for the temperature of Eastern Colorado, you would absolutely notice that. It's like moving 600 or 800 miles south. Around here, we don't have to go 800 miles south to see a difference in climate. All we have to do is go uphill, right? So we live down here on the Great Plains, and then there's foothills and mountains and snowfields and stuff. Every 10 degrees Fahrenheit is like going 3,000 feet up in the mountains. So you could imagine like the temperature of Denver moving up to Rocky Mountain National Park, or the temperature of Estes Park moving up to the top of Trail Ridge Road. I mean, this is like a huge change. This is about how much change happened at the end of the last ice age, but that change took 100 centuries to happen. And we're talking about doing it in 1 century. So a monster, huge change. Now, it happens that we live in a region that's very vulnerable to climate change because we don't have extra water to go around. So here's a map of the precipitation in the Western US, and the brown places are brown and the green places are green. We got 75 million people who live in the Western US, and we get almost all our water from these little blue places on the map. Those are our mountains, right? The mountains collect the snow as the water as it goes by, turns it into snow. And then every spring, like clockwork, the snowpack melts and down comes the water and fills up our reservoirs. And that's like a giant water tower that's up there collecting our water. If we switch out the climate of Pueblo for the climate of El Paso, what do you think is going to happen to all that snow? But wait, it gets worse. Not only is there less snow, there's more water demand, right? So if you like on a hot day in the summer, your lawn needs more water. Similarly, the crops need more water, the livestock needs more water, the forest needs more, everybody needs more water when it's hot. So if you cranked up the temperature to be like El Paso, you would want way more water than we have. And that makes it much, much more difficult to meet the balanced supply and demand. The other thing around here that's such a big deal is wildfire, right? We have warmer air that evaporates more water out of our forests. There's also a longer fire season, a longer warm season. You start getting like water use in May instead of June, and maybe your fire season runs out into October instead of September. And then lastly, you know, those really bad fire days when it's like 99 degrees in the shade and 5% relative humidity and it's windy and they have to evacuate the firefighters and it comes down into neighborhoods and stuff. Those days happen way more often when it's hot than when it's cold. So just here in Colorado, we expect it for every 1 degree Celsius of warming, about a 600% increase in wildfires. And here we're looking at something like 5 degrees Celsius of warming. So something like a 30-fold increase in the amount of wildfire. In fact, you get to the point where you're burning the forest down faster than you can regrow it, and then you just don't have forests anymore. So it's kind of grim. What are we going to do about it? Well, there's basically one thing we can do to prevent those terrible outcomes, and it's stop setting stuff on fire, right? This is kind of the obvious thing. The way we make all that CO2 is we dig up a whole bunch of carbon out of the ground, we set it on fire, it turns into CO2. So how are we going to do this? I mean, I'm being a little facetious saying stop setting stuff on fire. But really, there's 2 ways to do it. One is to live well with less energy. And the second way is to make energy that doesn't involve setting stuff on fire. So here's sort of an example of the first way. Buildings. It turns out we use almost twice as much energy in buildings in the United States as we use in cars. Buildings, we thought back in the bad old days of like 2005 and 2010 that we would use more and more and more energy in our buildings out to 2030. And every year when the Department of Energy sort of assesses our energy needs, it comes way down. In fact, just this one change alone is saving us in the United States $4.5 trillion over the next decade in energy we were planning to waste. And it turns out we don't have to waste that energy, right? We got better doors and windows and lights and furnaces and air conditioners and all kind of stuff. So we don't waste as much energy and we save boatloads of money. And what we got to do with that money is invest it in better ways of making energy so that we're not putting CO2 in the air that way too. Look at what's happened to the cost of solar power. Just in the last 10 years, people were forecasting like way the hell out to 2050 that solar was going to cost, 10 cents, 12 cents a kilowatt hour for power, just like what it costs now or used to cost for coal and gas. But what's actually happened in the last decade is that the price of solar power has fallen down to like 5 cents or even 3 cents a kilowatt hour, way less than the cost of coal, oil, and gas. So the costs of solar are about 200 times less than when I was in high school. I mean, I remember being in high school. It doesn't seem like that long ago to me. Imagine if cars were 200 times cheaper than when I was in high school. I mean, 200 times, that's unbelievable. 5 times cheaper just in the last decade. So it's going to cost some money. Economists estimate that switching over the whole world off of fossil fuels will cost about 1% of the global economy. $1 out of every $100 on Earth. That's a lot of money. That's about what our ancestors spent to retrofit all the world's cities with indoor plumbing. Think if you had to do that today. Think about the labor costs alone. If you had to like dig up every street in New York and London and lay sewer pipes and knock out tenement walls 20 stories tall and put in hot and cold running water at like union labor rates and knock out the partitions inside every apartment and put in toilets and sinks and showers. But boy, are we glad they did that, right? Because we got toilets and sinks and showers. And not only that, what did it do for plumbers? What did it do for plumbing suppliers? What did it do for the grocery store down the street from the plumber or the children of that plumber who could use that money to go to college? That was totally worth it. And that's how innovation works. These are my grandparents. That's Max and that's Francis. And it was their generation that did the giant indoor plumbing thing. When they were done with indoor plumbing, they did rural electrification. Imagine what it would cost to run a separate copper wire to every farm in Nebraska, right? And then when they were done with that, they fought the Nazis and, this is greatest generation. These are my parents. That's Margie and that's Bob back in the 50s. And their generation did great things too. Giant 1% of the world economy kind of projects like interstate highways, the Cold War, going to the moon, for God's sakes. None of these things ruined the economy. They actually were the economy when my parents were young adults. This is me and my wife back when I had hair. And our generation did ginormous things too. We put computers on every desk on Earth over and over, like trillions of dollars on PCs. And then when we were done with that, we trashed all the landline phones in the world and replaced them with cell phones. Oh, by the way, we also built the internet. All of these were 1% of the world economy size projects, and every one of them created all of the jobs and prosperity in my adult life. That's how this works. These are my kids. That's Matt and that's Nate, and they get to do it again. They get to replace old crumbling infrastructure with smart grids and solar panels and wind farms and batteries and better transmission, all kind of stuff that's going to make the world a better place. And that's going to produce all of the jobs and prosperity in their adult lives, just like the internet and cell phones did in mine. You can choose 2 ways to think about your future. You can think that our well-being comes out of the ground, that it's based on extraction, that every dollar in the world comes from burning stuff that we dig up. And maybe that's true, but God, what a disastrous way to look at the world, because what happens when you run out? What, the whole world goes back to the Middle Ages? What a terrible way to look at history. I prefer this. We create our well-being. We do it from our creativity, ingenuity, and hard work. It doesn't come out of the ground. It comes from the sweat of your brow and the sparks in your soul. And we're not running out of that stuff anytime soon. And our kids can have a bright future just like we did. Thank you so much for your time. And I'm sorry that we have to be done, but have a great meeting and keep doing the wonderful work that you do. How do I stop sharing? Right there.
Oh my God, that was wonderful.
Good.
There I am. I'm unmuted. I was trying. This technology, boy, you'd think after 100 Zoom calls.
Yeah.
Dr. Dunning, that was so great and it was so easy to understand. Thank you so much. And I love the comparison with the plumbing changing. I mean, really.
Every generation has done this stuff, right? Since the Middle Ages. Think about like horses and buggies, right? They were cheaper than cars, but we bought cars anyway. This is what we do. We get rid of old stuff and we replace it with new stuff that works better. Get
Well,
over it.
we had expected, I had given you more time, Dr. Denning, so.
Oh, I thought you said 20 minutes.
No, I said 40, but listen, no, that's okay,
I screwed
but
up.
that's okay. We have time for some questions then.
All right, I'm
If
sorry.
anybody-
Roz,
No,
I'm
that's
terribly sorry.
okay.
I thought you said 20 minutes.
No, that's okay. Listen, people will be happy to leave early.
All right, well, I got plenty
Yes,
more. You got questions? You want me to talk about stuff? What do you got?
Okay, so let's do questions by, I guess we'll try the raise the hand method, I suppose.
Or just shout them out. There's not that many of you.
Okay, can
So
they
what are
unmute themselves?
What's the lowest fruit? What's the lowest hanging fruit? Is it electrification of everything?
Yeah, well, so yeah, I think we are going to electrify everything in the next 10 or 20 years. You're going to see gas furnaces being replaced by air source heat pumps. You're going to see, actually the lowest hanging fruit is always not wasting energy that you were planning to waste, right? So like insulation and better cars and better windows and all that kind of stuff. Electrification is huge. I mean, that's going to take some doing, right? Electrifying the transportation fleet, that's going to be a big job. We have to have better batteries to do that. Electrifying stuff also, the sun doesn't shine at night and the wind doesn't always blow. So part of the deal there is distribution grids, right? So you want to be able to have much better power grids so that, like that thing that happened in Texas this week doesn't happen, right? You want it to, Texas ought to be able to use electricity that's generated in Arizona or Iowa or whatever, where you can move electricity around from place to place. Doing that is hard because you use AC power that only goes, maybe 300 miles on a wire. Have to have an interstate of electricity. You'll still have AC power in your house, but there'll probably be high voltage DC lines to carry juice from say the Arizona desert to New York City, or from the wind farms off the East Coast to Iowa for that matter. So I don't know, the low hanging fruit is usually doing stuff that saves you money right off the bat, Manny, you had a question.
Yes, thank you. I'm not sure if you're familiar with the work of architect Buckminster Fuller.
Yeah.
He wrote a book a long time ago, back in the 70s, I believe. It was called Operating Manual for Spaceship Earth. And in this book, he posited the fact that prior generations, back in the time when seafaring and pirating and so forth was popular, men and women, but mainly men of that time, had a global outlook. It was not so much a nationalistic outlook as much of a planetary outlook. And so they viewed the world as a global village. And my question to you is, how can the scientific community internationally, the international scientific community, put together some call for a different outlook of our nation? Right now, the United States and China and Russia and everyone is working on their own plan, so to speak, in the Paris Climate Agreement. But I think what we need is a global plan, and we need to stop thinking about nations and start thinking about a planetary society and how, as a global society, we can solve those problems. And I think the call for the scientific community to clamor for that is what's necessary, because especially
that sounds good if scientists were in charge, Manny, but I have to say, what you're talking about is really sort of the political organization of the world. And sadly for me, scientists are not in charge of that, right?
But what I'm asking is for scientists to get together and call for this kind of consciousness to come forth.
So I tend to agree with you. And I think that global problems require cooperation, right? For example, look how poorly COVID worked out when everybody went their own ways, right? If we had a global virus, a global pandemic, and international cooperation goes a long way with global problems. Certainly, we all share the same air. If you burn a lump of coal in Pueblo, the CO2 from that coal is in China in a matter of weeks. Similarly, if you burn a lump of coal in India, the CO2 from that is over Colorado in a matter of weeks. We all share the same air. There are no international boundaries in the atmosphere. So you're right. We have a kind of a common problem, and maybe we need common solutions. And I think to some degree, countries have come together, right? I mean, we had an immense effort since the 1990s to negotiate these targets, and the countries of the world signed an agreement in Paris in 2015, 194 countries. So it's a huge thing. But it's still kind of fragmented. I wish I had the answer for you. I don't really have a way to fix that. But I hope to God we fix it, because we have a big problem, and it matters. It matters for us, and it matters for our children.
Thank you.
Anyone else?
David.
Dave?
Yeah, Scott, thank you from me as well. Great, straightforward discussion of the physics, and I really appreciate your optimism too, which is hard to balance, and you did a nice job. Actually, I have two questions. First one is just, I wonder if you've got any insider takes on new technologies for cement manufacture or cement substitutions.
Yeah, it's kind of outside my my real expertise, but I have been reading about alternative formulations for cement, and particularly alternative, but both alternative chemistries and also alternative processes for making cement. I think there's a lot of work on substituting other, so that you're not using carbon. I mean, basically cement. You start with calcium carbonate, and you drive off the CO2 to make calcium oxide, that then is the thing that holds concrete together. So right. I think there's work on the concrete side, which is maybe involved with different aggregates, and also sort of synthetic, the glue part, the part that holds it together. But it's kind of outside my real expertise. I don't know that much about it. It's about 5% of CO2 emissions globally is making cement, as opposed to burning fossil fuels. Yeah,
which is makes it a big deal, you know.
Yeah, it is a big deal.
We'll get that figured out. Well, my second question is just wonder your stance on nukes, especially the new technologies that seem to.
Yeah. So remember, I said the big thing is to stop setting stuff on fire. And so nuclear power is actually a way to make electricity without setting stuff on fire. You basically have rocks that get hot, and use the heat from the rocks to boil water. And we know how to do that, and we get quite a lot of electricity out of it. Unfortunately, people are worried about the waste, and about what you do with the waste. And the other thing about nukes, it's incredibly expensive. It's much more expensive to make nuclear electricity than it is even to burn coal. So you have to sort of weigh these things. I tend to think that a very rapid decarbonization, if we really get rid of fossil fuel, we may benefit from having nuclear power online. In fact, maybe one of the most important parts of that is not turning off the nukes we already have, that we already paid all that money for, that are generating all this electricity. It's something like 20%, 15 or 20% of the electricity in the United States comes from nuclear power. And almost all of those plants are reaching the end of their lives. So they're coming up on being decommissioned. And if we take them all offline, that means we have even more of a demand to scale up solar and wind. So, and then you mentioned the new technologies. There's small modular reactors. There's a whole new wave of these technologies that are intended to be much safer and much cheaper, because the current design that goes back to the 1960s, 1970s, I mean, it's like $10 billion to build a nuclear power plant. And it takes many, many, many years for that to pay for itself, even charging, 20 cents, 30 cents a kilowatt hour for electricity. So it's a tough one. It's over my pay grade, right? This is one of those socio-political questions more than a science technology. I think we can make electricity without setting stuff on fire. It winds up really being a question for everybody about what do you want to do about this? Do you want nuclear power to be part of your portfolio going forward? Or do you want to scale up solar and wind and batteries and transmission lines way faster because you're shutting down the nukes? It's a tough question. Sorry if I didn't really answer you on either of those, but I did the best I could.
We got a feel for your thinking about it.
Excellent
That was
question.
Thank you. Thank you very much.
Well, I don't know if you're aware of it, Dr. Denning, but Pueblo County and Pueblo City in 2018 resolved for 100% renewable for everyone by 2035. So that was a Sierra Club, at least the one in the city, a Sierra Club
So impressed.
campaign, and
they've very forward thinking.
Amazing, really.
Fort Collins is doing a similar thing. We own our own electrical utility, so we have we have a lot more flexibility than most American cities. There are 4 cities in the Northern Front Range. It's Fort Collins, Loveland, Longmont, and Estes Park that together own a big power utility, Platte River Power Authority.
Believe me, we looked long into Fort Collins when Pueblo was trying to transition to public power as an example to follow.
It's amazing. I was part of this committee, and we had the CEO of Platte River Power came to our meeting. It was a citizens committee, is convened by the city government, and this guy looked me in the eye, and I had said, well, what, we want to shut down the coal-fired power plant, and he looked me in the eye and he said, "You are our owners. If you tell us that you want to shut that power plant down, we're shutting it down." I'm like, oh, amazing. And they're going to shut it down by 2030. So we're going to have 100% non-carbon power by 2030 in Fort Collins. Now, there will be people trying to weasel out of it. We will see. One of the things that I think you'll wind up seeing as well is you start hearing this argument that, well, we already own this thing, this coal-fired power plant. It's worth $1 billion. Maybe we should just sell it, or maybe we should rent it to somebody, and somebody else can take the blame for releasing all that CO2, and it won't be our fault anymore. So all these kind of weaselly things that people come up with to get out of these, and we are trying to pressure our own utility to actually mothball the plant, to shut it down, not keep it running and sell the power, but really turn it off.